Hello, everyone. Thank you for being here, and thanks to the organizers for putting up this meeting. I apologize in advance if my voice is not on point or I cough a little bit, but I caught a cold this week, so my throat is a bit fragile. Okay, so I introduce myself. I'm a PhD student at Universidad de Buenos Aires under the direction of Cecilia Canapiego and Sebastián Nusa, and I'm going to talk about the work we've been doing recently, which will hopefully be published soon. The work is titled Kinematics of the Local Group Gas and Galaxies in the Hestia Simulations. So let me start by providing some context and motivation for this work. The local group's two major galaxies are the Milky Way and Andromeda, or M31, which are on a collision course. The local group is also composed of several smaller galaxies and intergalactic gas, and of course dark matter. And due to gravity, most of the galaxies in the local group are expected to have a general infalling motion towards the local group barycentre. The gas dynamics is much more complicated, but we expect a general flow towards the barycentre too. But the main drivers of the overall kinematics of the local group are the Milky Way and M31 themselves. One could picture them in falling and kind of dragging the intragroup medium and smaller galaxies with them due to the strong gravitational pull. And as a result, the gas behind them, that would be the gas in the outskirts of the local group, tends to lag behind with respect to the Milky Way, to M31, and as they run into the gas that is between them. So from our position in the Milky Way, looking towards the local group barycentre, we should see gas approaching us with a negative radial velocity, and gas behind the local group barycentre should be receding from us. So it should have a positive radial velocity. Now, there is observational evidence of a radial velocity dipole in the general direction of the local group barycentre as viewed from the local standard of rest. This evidence comes from the Hubble Space Telescope Cosmic Origins spectrograph. But coincidentally, the Sun's rotation around the Milky Way contributes to this dipole moment, even though the contribution is very small for high latitudes. The contribution of the Sun's rotation around the Milky Way is small for high latitudes, and the dipole pattern persists at high latitudes. So this could indicate that at least part of the gas being probed belongs to the local group far beyond the Milky Way virial radius. So in this work, we analyze 3 high-resolution local group simulations from the Hestia project to see if they reproduce the observed trends. This is a projection of the gas mass in the 3 simulations to give you a general picture of them. And throughout this presentation, we will order them by ascending infall velocity of the 2 main galaxies, them being 9, -74, and -102 kilometers per second. For the 3 simulations, which are called 3711, 918, and 1711. So in the 2 last ones, the galaxies are approaching each other, and in the first one, they are receding slightly, but a very slow velocity, so they are pretty close to turn around and to start the infalling motion. So to locate the Sun in the simulated galaxies, we place it in the Milky Way disk at a radius of 8 kiloparsecs and at an angle such that the M31 position matches the observed galactic longitude. That would be 121 degrees. And we also assume that the velocity of the Sun around the Milky Way is purely tangential in these simulations, and it is given by the Milky Way's rotation curve for each simulation. And these maps show a neutral hydrogen column density distribution inside, to the left, and outside the Milky Way for all 3 realizations. The green cross indicates the barycentre direction, while the red cross indicates the anti-barycentre direction. That would be the opposite direction of the barycentre. And you can see M31 in the 3 realizations, pretty near in position to the barycentre position in the sky. So from this Sun's position, we plot these rectangular maps of radial velocity of the gas outside the Milky Way, as seen from the local standard of rest. So this is filtered to not include galactic gas. We also mark smaller galaxies with circles in this plot. The velocity dipole is evident in all simulations, but remember that the sun's rotation around the Milky Way contributes to this dipole at low latitudes. So at high latitudes, the dipole shows more clearly in the two simulations in which the Milky Way and the M31 are approaching each other. That would be 918 and 1711, the middle one and the lower one. We also see that the galaxies show a similar pattern to the gas. So here we can see how near the poles or high latitudes, we can see mostly receding material and approaching material in the corresponding hemispheres. So here we have the barycentre in the southern hemisphere, and material in that hemisphere tends to be approaching us, and material in the other hemisphere tends to be receding from us. The other way around in the 1711 realization. In the first realization, it's not so clear, but this is kind of expected because galaxies, the two main galaxies, are not infalling in this realization. So this brings up the question: what happens if we eliminate the galactic rotation from the velocity field? And for gas outside the Milky Way, the dipole pattern is evident in the two infalling realizations. Remember that we are ordering these realizations by ascending infall velocity. So in the 3711, where the galaxies are not infalling, a dipole pattern is not evident, but in the other two, there seems to be a dipole pattern in the direction of the barycentre and anti-barycentre. And this pattern is clearer in 1711, in which the galaxies are approaching faster. So when transformed to this frame, that is called the galactic standard of rest, that is removing the sun's rotation around the Milky Way, there is a clear relation between the dwarfed galaxies' velocities and their position in the sky. We visualize this clearly in this radial plot of GSR velocity versus distance from the Milky Way by color-coding the angle between the other galaxies and M31, as seen from the Milky Way. A clear trend appears, and galaxies in the M31 direction, and that would be blue circles in these plots, appear to have more negative velocities than the ones behind us. That would be yellowish dots. Okay, so we can see that this trend even persists at around 2 megaparsecs, which is quite impressive, and this kind of goes with the expected behavior that galaxies in the direction of the M31 are approaching us, and in the opposite direction are receding from us. In red, the line marks the average behavior of gas in the local group, and the dotted line marks the Hubble's law for reference. If we unfold this gas between gas in front and gas behind the Milky Way, we see that a similar trend appears for the gas in the local group. And that would be that the gas in front, which is plotted here in blue, tends to have more negative velocities in all three simulations than the gas behind us, which is plotted in the red line. The shades here mark up to 1 standard deviation. We could take this a step further and remove the Milky Way peculiar motion through the local group by transforming velocities to the local group standard of rest. So this gets rid of the imprint that the Milky Way's motion has in the velocity sky, and we can see that there's a significant narrowing in the distribution of velocities for the gas and the galaxies in the direction of the barycentre and the anti-barycentre direction. So in this plot, we plot the distributions of sidelines in the quadrant containing the barycentre and the anti-barycentre, and we see that there's a significant spread before converting to the local group standard of rest. And this narrowing is expected for material outside the virial radius. So it supports the interpretation that the gas being observed belongs at least partly beyond the Milky Way. So this is gas in simulations and galaxies in the simulations. So to conclude, we see that the dipole pattern is visible from the local standard of rest in the three realizations. We also see that removing galactic rotation makes the pattern of a dipole persist in simulations in which the galaxies are approaching. And from these three simulations, we consider 1711 to be the one that best resembles the kinematics of the local group, as it shows the clearest dipole for group standard of rest velocities, and also a bimodal gas distribution. I forgot to mention that, but the Milky Way, the gas outside the Milky Way shows a bimodal distribution even when seen from the local group standard of rest, when you probe in the directions of the barycentre and the anti-barycentre. That identifies gas falling towards us and receding from us from each of these two directions. And in a follow-up work, we will also examine quantitatively how different ion species contribute to this gas kinematics, which can further provide a comparison between simulations and observations. So thank you. That was all.
Thank you. For questions? Have questions from the remote participants? Okay, if there are no questions, one question.
Yes, hello, Luis. So, I think, could you extract some information about the dark matter content in this relation you have found from this approaching of galaxies in the inner region of the inside region of this approaching from your simulations?
Okay, so we didn't explore dark matter movement in this work because it doesn't have the best correlation to be made with observations, and that was the kind of the idea behind the motivated this work. But it could be done. I'm sure that it would be a pretty similar motion to that of the galactic halos that clump up on the dark matter halos. But the thing is that I think it would be kind of difficult to find an observational counterpart with the kinematics of the dark matter.
But my comment is relating because most likely your result will depend on the potential well, underlying potential well, which is a cosmological model dependent. So maybe, I don't know, if you change the setup, cosmological setup, the underlying dark matter, the underlying potential caused by the dark matter may have some changes in your picture.
Oh, so you are suggesting simulations with an alternate cosmological model? I don't think I understand